So welcome everybody to today's special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have Professor Piotr Indyk as our speaker. Piotr is the Thomas and Virginia Kabab Professor at MIT. He's best known as the co-inventor of the locality-sensitive hashing methods and the sparse Fourier transform algorithm, and has also made extensive contributions to streaming algorithms, clustering, sparse recovery, and learning theory. Piotr is a fellow of the ACM and the recipient of the Packard and Sloan Fellowships. Additionally, he served on the editorial boards of the Journal of ACM, Science Journal on Computing, and the IEEE Transactions on Signal Processing, and was the chair of the program committees of ACALB and SODA. Today, Piotr will tell us about learning-based sketching algorithms. Please welcome Piotr Indyk.
Right, thank you for a very nice introduction and for inviting me in the first place. It's a great pleasure to be here, at least virtually. So in this talk, this talk is about algorithms for streaming and sketching problems. Problems such as frequency estimation, heavy hitter detection in data streams, and nearest neighbor search. And the distinguishing feature of this algorithms is the learning-based, which means that they use machine learning methods to optimize their performance. So before I start talking about our contributions, let me start from explaining a little bit more what this learning-based what does learning-based mean? So this is an area that has been developing over quite a while. It goes back to back almost 2 decades, and it's a very diverse area. There are many approaches of using machine learning to improve algorithms, but at least from my perspective, it's apologies. At least from my perspective, it can be roughly classified into 4 groups. So the first group goes under the name of algorithm configuration. And here is an idea that the idea is that many algorithms have some knobs, various parameters or selection choices, which can be optimized to improve their performance. Right, so a prototypical example here is Satzilla, which is a portfolio, a collection of SAT solvers. And here, the knobs are just various algorithms, different algorithms for solving SAT, and their, the parameters of those algorithms. Right, so the work of Leighton Brown and others from the early 2000s, made a major contribution to this area. And recently, Gupta Ravgarden and Nina Balkan made contributions to theoretical understanding of those methods. Another example or another class of machine learning-based algorithms, which is similar but conceptually and qualitatively different from algorithm configuration, is based on so-called prediction oracles. Right, so prediction oracles are machine learned oracles, which can be trained using past data and can be called at any time during the runtime of the algorithm to provide some useful information about inputs or part of the inputs. Okay, so these are particularly natural and useful in the context of online algorithms, because in online algorithms, the algorithms have to make decisions based on seeing only part of the input. They don't know the future. So the work of Likoris, Vasilvitsky, and others shows that even if you have some partial predictions about the future, it can help algorithms, for problems like caching and others. And they have been also useful in the concept of data structures, branch and bound algorithms, and so on. The third class can be termed learned structures. This is not a standard name, it's just a name that I found useful to depict this class. And here is the idea is that this applies to algorithms which rely on some mathematical structures, like for example, matrices or functions or similar objects. And in classical algorithms, those objects are typically chosen at random, you know, like a random matrix to perform projection. But in these algorithms, those structures are optimized based on the data to improve over the random choices. Right, and here the practical example is a work termed learning to hash. We started from the work of Salah Khudninov and Hinton, where the goal is to provide a short, distance-preserving summary of high-dimensional objects. And more recently, it's been also very popular in compressed sensing. And the last example, or the last class, is often called the end-to-end algorithms, which are algorithms which are completely implemented end-to-end as some classifiers, right? In particular, recurrent neural networks. Okay, so here the idea is that those neural networks are given examples, right, of the input-output pairs, and the algorithm is essentially inferred based on these examples. So this approach has been particularly popular for in optimization, for problems like scheduling, TSP, and machine learning. All right, so this is roughly the space of learning-based algorithms as I see it. There are several other names which are very closely related. They mean something different, but data-driven is also a very popular ways to refer to those algorithms. Now, the two algorithms that I will describe today fall into these two classes. Okay, so the first algorithm for streaming algorithms falls into the prediction oracle class. It creates, learns, and then utilizes machine learning-based predictors to improve the performance, to reduce the space, improve the accuracy of the streaming algorithm. And the second example falls into the learn structure class, where the idea is to optimize locality-sensitive hash functions, again, based on the. All right, I forgot what the protocol is. I guess people raise their hand, right? If they have any questions.
Yes, or you can pause for questions, I guess.
I see, okay.
Either works. Are there any questions so far? I guess not.
All right. So let's start with the first result. So this is a learning-based algorithm. It's a streaming algorithm for frequency estimation. Okay, so let me start by defining the problem. And this is has nothing to do with learning yet. Like this is a classic problem in data streaming literature. So the goal of the frequency estimation is as follows. We are given a stream, a data stream, which is a sequence of elements from some universe U, right? So in this example, the universe is just, digits from 0. Well, I guess they are not digits because there's 10. Okay, it's a bunch of numbers from some range. And the goal of the algorithm is to make a single pass over the input, right, from left to right. And after this pass is performed, the algorithm has to support the following functionality. Given any item from the universe, it has to report an estimation, f tilde I, of the frequency of that element in the stream. Okay, so for example, the frequency of the element 1, right, would be 1 because there's only one in the stream. Okay, so this is the problem. It's essentially counting, right? It's counting. The problem involves counting of the elements in the stream. So of course, counting is a useful tool, right? So it's not surprisingly, this problem has many applications in many areas of computer science, machine learning, and beyond. And now, of course, this problem is essentially trivial if you don't have any other constraints, right? Because if you are allowed to use a linear space, then you can simply create a hash table, right? Or just a table which are for each element counts exactly the number of times this element occurs in the string, right? Unfortunately, you cannot do it in many applications because the data sets are too large. So then the challenge becomes to do something similar, but using only a sublinear amount of space. Now, of course, in that case, you cannot get exact counts. However, there has been lots of research which shows that you can get pretty good estimations of the true frequencies with a controlled error and using a sublinear amount of space. Okay. So this is the frequency estimation problem. It has been studied for the last 2 decades, at least. And the algorithm that I will focus on in this lecture is a so-called count-min algorithm. Okay, so what's the algorithm? The basic component of this algorithm is very simple, and it looks as follows. Okay, so first, the algorithm hashes the whole universe into a much smaller range, such that the elements in this range can be counted exactly, and then does exactly that, right? So the algorithm makes a pass over the data. It maintains the counters, the array of counters. The size of this array is controlled. It's a parameter, and of course, the longer this array is, the higher quality approximation you get. And in each entry of this counter, the algorithm maintains the sum of all of the frequencies of the elements that are hashed into that array, right? So this is exactly the formula that for the content of the jth counter, right? You just sum up all the frequencies of all the elements which are hashed to this particular cell. And it's not difficult to see that this array is very easy to maintain in a streamic model, because every time you see an element I, you simply increment the counter, you hash I and increment the corresponding counter. Okay, so this is something you can do in a single pass, and the amount of memory used is basically controlled by the size of the counter table that you are using. Now, this is the basic algorithm. More general versions include several arrays of counters. Okay, but it's not that relevant for the talk today, so I will mostly skip it unless somebody has questions. Now, finally, how do we estimate the count of a given index I? Well, we simply take this index. Oops. We simply take this index, hash it again, and we return the count stored in this hashed bucket. Okay, so the value in this hashed of the value in the bucket that I is hashed to is the reported approximation to the true frequencies. Okay, so you can see that this approach induces some error, right? Because the frequencies that are hashed into this bucket, involves I, but also potentially some other frequencies, right? So therefore, this is not an exact algorithm, it's an approximate algorithm. But by controlling the number of counters, we can control the amount of noise that corrupts our estimation, right? So we can get trade-offs between the accuracy and the amount of space. All right, so that's essentially the whole count-min algorithm. It has very nice properties, which is why it's widely used. In particular, it works both with insertions and deletions, right? So deletions are implemented just by decrementing the counter as opposed to incrementing. Furthermore, it has this very nice property that the estimation never underestimates. Okay, it can overestimate if some other elements collide with the I, but they never underestimate, assuming that all the frequencies are non-negative. And this is very useful in property in many applications. So this is the main algorithm that I will focus on in this talk. However, I will also briefly talk about another algorithm very closely related called the count sketch. And count sketch is essentially the same as a count min, with the difference being that essentially arrows have signs. Okay, so when we sum up all the frequencies that are mapped, of the items which are mapped to a given bucket, they can be multiplied by a positive or a negative sign. Okay, which means that in count sketch, errors cancel out, or potentially can cancel out, which generally means that the expected error of a count sketch is smaller, right? Because things don't aggregate. But at the same time, they don't have this no underestimation property, right? Because the error can go both ways. So depending on the applications, people use counting or count sketch, depending on how useful this property is in a given scenario. All right. Any questions about these algorithms?
Are there any questions? If there are any, feel free to type in the chat box or use the raise hand feature.
Yeah, unfortunately, I don't see chat box on my screen.
Okay, I can read them out, but
you can read them out. Okay. Good.
Yeah, but there aren't any questions. Yes.
There are any questions so far? Everything is clear. Okay, excellent. Good, good, good. All right. So now the question is, how can we take this algorithm, right, which does not involve any learning, and how can we augment it with machine learning methods to improve its performance? So in order to do it, it's worthwhile to have a thought experiment. Just think, what are the possibilities, right? What are the type of, what is the information in the data that a learning-based algorithm can potentially use in order to improve the performance of the algorithm? And if you think about it for a few minutes, you can see that indeed there is potentially quite a lot of information in the data that can be used. Okay, so for example, count mean is often used for word data, right, where the stream is just a stream of words. And for words, we actually know various statistics about word corpora. In particular, it's known that word frequencies tend to be inversely correlated with the length of the word, right? Long words tend to be less frequent than short words, okay? So this means that, just by looking at the ID of the item, you can make some preliminary inference about the frequency of that word. And similarly, if you look at the other applications in networks, obviously some IP addresses or IP domains are much more popular than others, right? So again, by looking at the ID of this domain, we can make some prediction or inference about the frequencies. So there is indeed now lots of potential information in the stream. And if you are able to gather this information, somehow represent it, then in principle, one can use it to improve the performance of the algorithm. And one potential approach is to use this information to avoid collisions with heavy items, right? Because every time your item collides with some other items, which is very heavy, which is very frequent, the error goes up, right? Colliding with heavy items, creates lots of error. So if we can use this information to maybe not eliminate, but reduce the collisions, okay, then this can indeed lead, at least in principle, to significantly reduced error. Okay, so this is essentially the main idea behind our algorithm. Okay, so let me now describe it in a bit more detail. So it comes from work with Chenyuk Su, Dina Katabi, and Ali Vakilian. It's inspired by recent work on Learn-Broom filters by Tim Kraska and Google folks. And its essence is to use past data to train a machine learning classifier, which is able to distinguish between heavy and not heavy elements. Okay. And once we are able to make this distinction, at least approximately, then the algorithm treats heavy elements different from the non-heavy ones. Okay. So pictorially, the algorithm is as follows. After we train this oracle, anytime we are given a stream, we run the oracle to detect whether it's heavy or not heavy. Okay. If the element is predicted to be not heavy, then we simply feed it to the standard sketching algorithm. Okay. On the other hand, if the algorithm is predicted to be heavy, that instead of putting it in the same sketching structure as others, it assigned a unique bucket, right? Meaning that the ID and the counter. And then it's counted, the number of its occurrences is counted exactly, okay? So in this way, the algorithms, the items that are for here are never mixed with those, okay? And therefore, we avoid collisions between these elements and these elements, which in turn help reduce the total error, okay? So this is a very simple algorithm, but it has a few very nice properties. And in particular, you can see that the algorithm, in fact, inherits worst case guarantees from the sketching algorithms that we use here, okay? Because, what can happen in the worst case, right? In the worst case, the learned oracle is bad, right? So it just hallucinates that some elements are heavy while they are not, okay? But the worst thing that can happen is just we are wasting those elements which were mistakenly classified as heavy. We waste the space to count them separately, okay? But this is something that we waste. However, we still retain the guarantees that comes from this algorithm. Okay, the guarantees might not be exactly as good as if we allocate all the space to this algorithm. But for example, if we split the space 50-50, right? Let's say we assign half of the space here, half of the space here. Then no matter what this learn oracle is doing, okay, we always get we always get guarantees on the error just based on the properties of this algorithm. Okay, so in a way, this algorithm has this nice property of being approximately the best of both worlds. If the learn oracle is good, then we avoid collisions between heavy and not heavy elements, and this significantly reduce the error. If the oracle is completely wrong, we waste some space, but we still retain some guarantees.
Okay, so we have 2 questions from the audience.
Sure.
The first question is from Vikash. The question is, how do we define the threshold between heavy and not heavy elements while labeling?
Right. So there are 2 ways of doing it. One is to, just parameterize based on the data, right? So, you learned during the learning phase, you also, figure out what is the right threshold to minimize the error. There's actually another trick, although it's limited only to insertion-only streams, which is, to assume that all elements are, to have the threshold really low, and initially identify all elements as heavy, but then, as you keep getting more data, some of the elements which were previously identified as heavy are relegated to the sketching method, right? So that there are various ways of doing it. But, conceptually, we can think that the threshold is also defined during the learning phase, right? With the goal of optimizing the trade-off between the accuracy and space.
Thank you. The next question is from Alan Liu. The question is, in network data, the IP address distribution is indeed very skewed, but which IPs are more popular than others keep changing frequently? Right. Are learned count min or count sketch overfitting to specific heavy hitters?
Right. So, so this is an answer that will be best, this is a question that will be best answered experimentally. Right, because we did experiments on IP data, so maybe I'll just defer the question to like
sure
2 slides from now.
Okay. Thank you. And the next question is from Andres Carrada. The question is, so in the worst case, if the oracle classifies everything as heavy, right, then the memory could explode in the worst case. Is that correct?
Right. So basically, you have to have a certain threshold, right? Yeah, I mean, the way you use it is, you know, in the end, you just bound the total amount of space used for each, right? And, you know, if you start using too much of one of the parts, you know, then you just move everything to the count sketch.
See, thank you.
Sure.
Those are all the questions.
All right. Yeah, it's a very good question, and you know, in many ways they anticipate the next few slides. So let me talk about experiments, because you know, ultimately it's an empirical algorithm. We also have a theoretical analysis, but you know, at the end of the day, the question is there structure in the data that the algorithm explores? All right. So we run our experiments on two data sets. One is a CAIDA data set, which is a standard data set for network traffic. It consists of a bunch of packets sent during some duration from you know, various sources to destinations. We focus just on the, I keep forgetting. We focus only on destinations. Okay, so we forget about the sources, but you know, similar experiments can be done on both. And these data sets consist of 1 hour of traffic, right? There's 30 million items. And we use the first few minutes for training and the remaining minutes for validation and testing, okay? So that's about IP data. Another data set that we use is this AOL query log data set, which consists of a bunch of search queries collected. That was a long time ago, I think 2004, by AOL over some period of time. And again, we use the first few days for training and the remaining days for validation and testing. Okay. So this is roughly how the distribution, frequency distribution in the data sets look like, right? So here you see, you know, this is the frequency of the most frequent item, you know, next to it, the frequency of the second most frequent item, and so on, okay? And this is plotting the log-log scale. Okay, so, you know, here you see a straight line, which means that, you know, it follows Zipf distribution. Here it's, you know, not quite a line, but, you know, it's pretty skewed as well. Now, in order to train this oracle, we use a recurrent neural network. You know, it's very natural in the context of word data, because words have different length. It's perhaps less natural for the IP traffic, but you know, it just turns out that that works pretty well. For CAIDA, we use a neural network with 64 units. For AOL, we have to use more. And we train it to optimize the error function, which looks like this. Essentially, what we want is want to minimize the expected error of the estimation, assuming that the items are chosen from the queries are chosen from the same distribution as the data, right? So, you know, if we choose element I, you know, this happens with probability proportional to Fi, and then we incur error, which is equal to this, right? Which is difference between the truth and our estimation. And finally, you know, we have to be careful about implementations, right? Because, you know, how do we measure things? So the way we do it is, you know, we measure everything in memory words. Count mean, like the standard counter, you know, just uses one memory word per entry of the matrix of the array. And the unique buckets cost 2 memory words, one for ID and one for count, okay? All right, so here is how our results look like. Okay, so there is quite a few plots here, so let me explain what's happening. So on the left, you see example performance of the algorithm in one of the minutes, and here one of the days. The results for other minutes and other days are comparable, right? So these are just samples. Here you see the results of experiments with the IP data, and here was the AOL data. Now you see there are two plots. There's a one for count sketch, and it's a learned counterpart, and one for count mean, and it's a learned counterpart. Okay, so let's look at this figure for starters. The others are similar. So the two main curves that you see here is this blue one and the red one. Okay, the blue one is a standard count sketch. The red one is our algorithm. Okay, and each curve depicts the error as a function of the space allocated. Okay, so the lower the better. Okay, because that means that for a given amount of allocated space, the algorithm has a lower error. And if you look at it, you can see that indeed this learning-based algorithm improves over the space of a standard count sketch. I'm sorry, for the same amount of space, it improves of the error of the count sketch, here by a factor of 2, and so on. Okay. So, so that means that this learning indeed helps. Now, what are the other curves? Well, this curve is our algorithm, but assuming that the prediction oracle is ideal. Okay, so of course it's not a realistic scenario, right? Because we just don't have it, but it shows that if we manage to improve the oracle, we can get in principle even bigger savings in space or accuracy. And finally, this dotted orange line here depicts an algorithm which can be thought as data-driven but not learned. So this algorithm simply stores all the heavy hitters found in the training data. Okay, so there is no generalization happening, right? It just stores heavy hitters that are found and then uses for the prediction. Okay, so you can see that it indeed does slightly better than standard count sketch, but not as well as the algorithm actually learns and generalizes. And we believe that this is because for IP data, this is about IP data, often the exact IP change, but the domains remain the same, right? So the learned algorithm, the learned oracle learns to ignore, the least different bits of the IP address and just focus on domains, right? Which so it's a very simple generalization, which we think helps with the performance. Okay. And here you have results for count mean on IP data. The results are qualitatively similar. The gap between learned and unlearned, non-learned algorithms are lower. And then finally, here we have results for the AOL, right? So again, you see there is some gap. However, for AOL, a table lookup does essentially the same as our learned algorithm, right? Presumably because there is less information that can be gained through the generalization. The only exception is here, right, where for a very large amount of space, okay, but for when the amount of space allocated is relatively modest, these two algorithms work essentially the same. Like both improve over standard count sketch, but the improvement is more limited. And finally, I should mention that this oracle also uses space, but this is the same space used for different runs of the algorithm, right? So in this graphs here, we count for the space used by the algorithm, but we amortize it over different minutes over different runs of this algorithm. Okay. All right. Any questions so far?
So we have one question in the chat box so far. So the question is from Devda Tupashi. The question is it reasonable to assume that there will be a bound on the amount of memory available? I assume he means the amount of memory that would be used, but
right. Well, yes. I mean, it's like this is the reason why the streaming algorithms are useful. Especially for applications like network traffic data. When you put things into the router, memory is costly. So people use a variety of summarization, sampling, count mean, and so on. For problems in computational biology, for example, K-mer searching, it's typically people try to run those problems on a single computer. So for efficiency, so also the memory is bounded. Yeah. Of course, if you don't have if you have unbounded memory, then you don't use those algorithms, right? Because in those cases you can as well count everything exactly.
Thank you. And I actually have a few questions. So
Sure.
just to clarify the setting, so the loss is defined with respect to a particular hash choice of hash function, or is it like, I guess at training time, do you, for every particular parameter setting of the neural nets, you would compute, right, what the count min would actually give you, and then you would use that as a loss for a particular choice of hash function?
Oh, I see. Okay, so that's a good question. I think that I might have confused things a little bit. So this loss function here is used just to define the predictor, right? So at this point, like this part here, the training part has nothing to do with the actual algorithm or the hash function or anything, right?
Okay.
This is basically, so this loss function, in fact, doubles as two things, right? Both as a loss function, which is used to train the neural network, and later as our error function that we use to evaluate the performance of the algorithm.
Okay, I
right?
see.
Yeah, that's a very good point, right? So this formula here serves two roles, right? And say formula, because right. So yeah, there's another thing that I forgot to say. In the end of the day, we actually do regression as opposed to classification, right? So we actually are predicting. We're actually, predicting those frequencies as opposed to classification. Yeah.
Okay, thank you. Actually, so we have a clarification regarding the previous question. So I guess what DevDA meant to ask was if there were bounded memory that should restrict the classifier as to how many it classifies as heavy. So perhaps it's asking sort of the thresholds, right? That you would choose depending on how many will be heavy.
Right. So the classifier currently, so that also, So basically what I sweep under carpet is that in reality, we don't do classification, we do regression. So basically, in a way, we are flexible with choosing threshold later because we get the prediction of the actual frequencies, which means that we don't necessarily have to decide the threshold during the training time.
Thank you. And I have another question. So in terms of the representation of the IP addresses, so here I suppose for the internet traffic estimation, there's probably some sophisticated way of actually representing that because the table lookup, is a lot worse than the learned methods. I was wondering what's the representation that you use that can, help the learned classifier to generalize.
Okay. Right. So we use a very dumb representation, basically just IPs as they are, basically as a sequence of bits. So we are not really doing anything particularly smart here, and it's actually quite possible that by using by doing anything that is remotely smarter, one could get a better performance.
Interesting. Thank you.
Yeah, it's a good question. Like at the end, we tried a bunch of things and this works. So.
I'm a little surprised that that's able to generalize in the right way. It's like
so we believe that like if you for example, if you just want to skip the least significant bits, then it's easy to do even if it's represented in this way, right?
Yes, right.
So yeah.
Interesting. Thank you.
Sure. All right. Okay, I think I have to speed up. Like I have to finish at 1:30, right?
Let's see, 1:40, 1:35 actually.
1:35.
Yeah, and 10 minutes at the end for questions.
Okay, so I have about 20 minutes. Okay, I think.
Yes.
No, I have. Yeah, 20 minutes.
22 to be exact. Yes.
Okay. All right, so this is the last slide about this algorithm. So after we got experimental results, we tried to figure out if there is some theoretical justification, and indeed we managed to analyze this algorithm under certain assumptions, right? So we assume that the distribution is a Zipfian, right? Meaning that the ith most frequent element has frequency proportional to 1 over I. And we also assume that the oracle is perfect. Okay. Now this assumption can be relaxed. We also get some results, but for now, let's just assume that we get a perfect oracle. So in that case, the whole problem is well defined, and you can just analytically estimate the expected error of both the classic count mean as well as learn count mean, again using a perfect oracle. And indeed, we can see that there is a gap between these two formulas. Essentially, what happens is that one term, which is logarithmic in n, is replaced by another term, which is logarithmic in n over b, where b is the total amount of space allocated to the algorithm. Okay, so when the total space that is allocated is relatively small, then these two logs are the same. But for example, if you allocate 10% of n, right? So for the relatively large amount of allocated space, then we have log of 10 as opposed to log of 1 million, right? So this at least conceptually helps explain that indeed there is a difference between these two algorithms because the expected error is actually smaller. Okay. And we also generalize it to the case when the oracle is not perfect. For example, it can make an error with a probability alpha, and then the bound is a convex combination of these two bounds, right? If alpha, the error probability is equal to 1, you get this. If the error probability is 0, you get this. And for other alphas, you get the convex combination of the two. Okay. And I should mention that this result is actually not in our original paper. It's in a follow-up work with Anders Amand. And I think this is all that I have to say about this algorithm. So unless there are very quick questions, I'm going to move on to the second part of the talk.
There aren't, yeah, you can go ahead and move on.
Okay.
There aren't any questions.
Perfect. All right, so let's move on to the second part of the talk, which is about learning-based algorithms for near neighbor search. Okay, so what's a near neighbor search? I mean, many people I see here worked on it on this problem before. So you are given a data set of endpoints. These are points in a metric space. In this talk, I will just focus on points in the Euclidean space. With some d dimensions, and we have two parameters. There is a distance scale, and there is approximation. Okay. So what we want is I want to preprocess this set of points, create a data structure, such that whenever this data structure is given some query point, another point in this Euclidean space, the algorithm quickly finds a point. Sorry, if there is a point in the data structure within distance at most r from the query, then the algorithm is supposed to find some potentially other point within distance c times r from the query. Okay, so this is an approximate formulation of the essentially range search in a high-dimensional space. Right? In the exact case, your goal would be to find a point within distance r, if one exists. In the approximate formulation, you can relax the distance to the reported points to be at most c times r. Right? When the c is approximation parameter, and this relaxation helps reduce the space of the query time of the algorithm. Okay. So this is one theoretical formulation of the problem. Later in this talk, I will focus on just approximate nearest neighbor, where there is no scale parameter. We just simply want to find approximately closest point. Okay. I will mention it when the switches happen, but for starters, we can just think about this problem as a theoretical formulation of what we want to solve. And needless to say, there has been lots of research about this problem over the years. I will not be able to cover even a fraction of those, so I will not attempt doing it. This research resulted in an algorithm with a space which is relatively small, ideally linear, definitely polynomial in n dimension, and you want your query time to be sublinear in n, right? So you want to avoid linear scan, and you also don't want to pay too much in terms of the dimension. All right, so this is the theoretical formulation that we look at, and this problem has been studied for a while, and especially in the case when the data lives in low dimensions, it has a very elegant solution using so-called Voronoi diagrams. Okay, so what's the idea of the Voronoi diagrams? You simply take your data set and partition the space such that you have one cell per data point, such that each point in cell has this point as its unique nearest neighbor. Okay, so if you compute this Voronoi partition, then similarity search or nearest neighbor just reduces to the problem of figuring out in which Voronoi cell your point belongs to, because once you identify the cell, you know what is the nearest neighbor. Okay. So this method works very well. You get a linear space, a logarithmic time after building some sort of a binary decision tree. The main problem is that unfortunately the performance degrades very quickly as dimension grows, because the space, the size of Voronoi diagram blows up exponentially in the dimension. Okay, so this thing works very well in low dimensions, but unfortunately doesn't work well once the dimension becomes large. Even for like 100, it just explodes. However, it turns out that this general idea of using space partitions to solve a nearest neighbor or near neighbor is actually quite useful. Even if you don't use Voronoi diagrams, and even if you apply it into the high dimension. Okay, the key idea is not to use Voronoi diagram, which gives you, one can say, ideal partitioning, but you get some cruder, potentially randomized partitioning. And the key properties of partitioning is that it should respect somehow the distances between the points, right? So typically close points should typically fall into the same cells, okay, and far points should typically fall into different cells, right? This doesn't have to happen always, but as long as there is some correlation between where the points fall into and the actual distance, then you can utilize those partitioning to get better outcomes. And equally important property of the subpartitions has to be that it's algorithmically easy. Basically, given a query point, okay, we should be able to very quickly figure out which cell of the partition this point falls into. And it's once we have such a partitioning, it's not surprising that we can use it to solve nearest neighbor. In the simplest case, we just look at the all the points which are in the same partition cell as the query point, and we examine them and report the closest one. Okay. So this approach has been, it's like the key idea behind many ideas. Perhaps it's closest to locally sensitive hashing and its neighbors, but it's also useful in other methods. For example, quantization methods, where this partitioning is obtained by selecting a bunch of points and then perform k-means clustering, right? And each cluster then corresponds to one cell in the partition, right? So this is very popular in the context of, for example, product quantization methods, right? Which rely on this approach. And in fact, if you look at other data structures, which are hierarchical, like random procession trees or PCA trees, at the heart of it, they also perform some partitioning. I mean, they do it in a multi-scale fashion, right? Start at the top and keep partitioning the space until you arrive at some cells, right? But at the heart of it, the goal here is to obtain, this distance respecting space partitions, right, where the partitions are somehow related to the distance. All right. Now, there are many other methods for computing for solving nearest neighbor, in particular graph-based methods, which performs a work on similarity search, actually often the most efficient ones, at least in the sequential setting. However, there's, the power of this space partitioning is particularly useful for a distributed scenario, where what you want is to distribute your points across different machines, right? Where each part of the partition corresponds to machine, and the objective is given a query assigned to one or a small number of machines, and then just run local nearest neighbor search algorithm in each machine. Okay. So here is where the partitionings are particularly useful, precisely because you can just associate each part with a machine. You can send your query in parallel to a few machines, okay, and you basically distribute everything in parallel, and you don't have to worry about sequentiality of the algorithm because all this process is very easily parallelized. Okay. So from this perspective, our goal will be as follows. What we want is to find a partition into some fixed number of parts, right, which is going to correspond to the machines that we want to distribute the data into, such that each part is balanced. It contains roughly, 1/n fraction of data points. And furthermore, typically, for a typical query point, most of its nearest neighbors, one or more, if you want to find them more, are in the same parts or in a small number of parts. Okay, so in this case, this approach, works because we can just send this query to one or a small number of machines and still get a good answer. And of course, we want this partition to be algorithmically simple. Like, we are not necessarily worried, super worried about the efficiency of this assignment algorithm, because in the distributed setting, communication is more important than the actual computation. But we still want this to be tractable, right? So we certainly don't want to scan the whole data to figure out which partition this query should belong to. Okay. So, we solve this problem empirically, but it's an approach which is inspired by recent theoretical developments due to these guys. I will definitely not do any justice to those results. I mean, it's a very nice work, but on a very high level, this paper contains two observations, which are actually theorems in those papers. The first observation is that nearest neighbor friendly random partition, in the sense of what I described earlier, are dual to sparse cuts in nearest neighbor graphs in a metric space. Okay, so essentially, one way to obtain such partitions is to take your data set, connect a bunch of nearest neighbor, compute the sparse cut, meaning a cut which cuts very small number of edges in this graph. And this is actually a pretty good partitioning in this nearest neighbor friendly sense. Okay. And equally importantly, the second observation says that such sparse cuts exist in any known spaces. And furthermore, can be made algorithmically simple, which means that to figure out which part a given point belongs to can be done without actually scanning the whole graph. Okay, so there is a much simpler oracle which assigns, geometric oracle, which assigns those queries to an appropriate part in this balance sparse cut partition. Okay. So again, I'm definitely not doing a justice to that paper, but hopefully I managed to convey the basic idea that we lived from that work, and we are utilizing it empirically. Okay. So how do we do it? Well, for starters, let's just think about a query to be uniformly distributed over the data set. It's not a realistic scenario, but let's just think about it, for the next 30 seconds. So in this case, can think that really the partitioning just reduces to the problem of computing this nearest neighbor graph and computing the balance partitioning, which are minimizes the number of edges cut, right? Because each time we have an edge like this, it means that the query, could be here while the solution is here, right? So each edge corresponds to an error. And what we want is to minimize the fraction of this error, which is exactly, balance partitioning of a given graph. Now, unfortunately, this assumption here is not realistic. Generally speaking, queries are out of sample. It can be anywhere. So we have to figure out somehow a way to take this balance partitioning and extend it to the whole geometric space, and in a way which is algorithmically simple, so that we can assign this query to one of those parts, without scanning the whole graph. Okay, and this is exactly where the machine learning comes handy. Okay, basically what we do is we treat the IDs of the partitions as labels. Okay, so we have blue labels for this part, red label for this part. And we train classifier which simply attempts to distinguish between these two parts. Okay, so in this particular case, it's a linear classifier. We just split into two parts. More generally, we have a multi-label classifier, so we split it in the multiple parts. But the idea is basically the same, right? We treat this IDs of the partition as labels, and we train classifiers to mimic the same partitioning, but in the geometric space. And by changing the complexity and type of classifiers, we can have a trade-off between how well this geometric partition approximates the original partition, and how efficient is to assign to run this partitioning, right? How quickly can we determine which part a given query belongs to? Okay, so this is our whole approach in a picture, right? We take the input data points, we perform space partitioning to partitioning to n parts to minimize the number of edges cut, and then we approximate that partitioning using a classifier. Okay. And of course, then in the query time, given the query, we run the classifier to figure out which part this query belongs to, and then we are done. Okay. All right. So this is high-level approach. Now a few details. So how do we do this partitioning? We use a software called the KHIP. We tried a bunch of things. In the end, we got best results with this approach. It's a very good code, right? Highly optimized, so it works pretty well. Now, for classification, we tried a bunch of things. We use linear models as well as small neural networks. Linear models naturally split things into two parts. So to get multiple parts, okay, I think I missed it. Right, so they naturally split into two parts. If you want multiple parts, you have to use a hierarchical partitioning using a tree. Neural networks are better suited for multi-partitions because you can just have as many output units as you want. And we use relatively small neural networks, okay, depending on the scenario. And finally, at the end of the day, we don't actually predict just a single part, but actually predict a ranking of parts, so that we don't have to look at just one cell, but we can look at some other cells. Okay, so this is related to like a various speed ups of. Let me actually skip that part. All right, so what are the data sets that we tried this approach on? We tried it on GLOVE and SIFT. Both are standard in the nearest neighbor search literature, roughly 1 megabyte size. Relatively, the dimension is high enough to make it a high dimensional problem, but it's not a super high dimensional. we use Euclidean distances, and we study the trade-off between the number of points which are retrieved from those partitions and accuracy, right? The more cells we look at, the more points we retrieve, and when we identify the nearest neighbor in those retrieved points, okay, the more candidates we have, the higher overall accuracy we get, okay. And finally, we compare to the bunch of baselines. We use a k-means clustering as one of them. It's actually a very good algorithm. And to test bipartitions, we use various algorithms which use hyperplanes. We use a random projection in the LSH style. We also use a PCA tree, two means, and a few other methods. Now, it turns out that at the end of the day, k-means clustering works best. So in the slides that I'm going to show, in the experiments I'm going to show, I would just show k-means because otherwise things are too cluttered. But everything else is basically worse than k-means, right? All right. So here are the results that we get. Okay. So what is happening on this graph? This graph shows a recall as a function of the number of retrieved candidates. Right, so more candidates means slower running time, but of course it means that we have more options to choose from. Right, so the higher number of candidates we get, the better recall. Right, so we are studying recall at 10, which is roughly the fraction of the true 10 the closest nearest neighbor that are actually appearing in our list of candidates. Okay. These two curves depict our method using neural networks as the classifier. And these two curves depict the best baseline, which is based on k-means. Okay. Now, the reason we have two curves as opposed to, so we have four curves as opposed to two is because we are measuring both the typical performance as well as almost worst case performance, which is the 95th quantile of the runs. Okay, so this is not quite worst case, but it's almost worst case, right? It excludes only 5% of the cases. And so, in a nutshell, you can see that these curves lie above these curves, which means that for the same number of candidates, we are getting better recall. Or alternatively, for the same recall, we get, let's say, a factor of 2. We can get the same recall with a factor of 2 fewer candidates, right? And you can also see that our algorithm performance in the typical and the almost worst case is more or less the same because we are, balancing the partitions by force. While k-means, there is no balancing happening, and this means that this almost worst case is slightly worse than the typical case. Okay. And here we get similar results, except that the improvement of our method over the baseline occurs only for this almost worst case as opposed to average. K-means actually in this case, for this data set, works very well on the average. Essentially, we don't improve anything, but we do improve in this almost worst case scenario. Okay. All right, so I think that this is the time I should finish. So let me basically skip all the other graphs. If there are any questions, I'll be happy to answer. This is the summary of what I showed, frequency estimation and partitions for nearest neighbor search. And, these are the natural conclusions. I find this work interesting, like this broader work interesting, because in principle, it offers us new techniques, which can be combined with the other algorithmic techniques to improve our performance. Right, but that said, we have to be mindful that there are both pros and cons, right? I focus on the pros, right? Better performance, but there are also cons, and they are quite important. And last but not least, there are a few pointers if you'd like to learn a little bit more about this field. And I think that I'm going to stop here. So thanks a lot for participating. And if there are any questions, I'll be happy to answer.
Thank you. Let's thank Piotr for the thought-provoking talk. So we do have a few questions in the chat box. So let me start with those. So first is from Devdat Dubashi. So is the number of partitions supposed to be known in the second part of the talk? What would happen if it's not?
Right. The number of partitions is supposed to be known, with the idea being that each partition corresponds to machine, right? So, the number of machines in your yes, number of machines in your system is known, and therefore, you design it with a particular number in mind. Now, that's a very good question. What happens if you are flexible about it? I guess you could optimize it together with everything else. And then you could just add the number of partitions into your objective function, right? Because I'm assuming the number of partitions is too small, then you have too many candidates to start from. On the other hand, if the number of partitions is too large, you might just not get, you might get lots of error because typically the query point and its nearest neighbor point would fall to a different partition, right? But yeah, it's a good question. I don't have a very good answer to that.
Thank you.
Sure.
The next question is from Samori. The question is, do RP trees work well on average? Are they boosted?
We are not running boosting variant in our original paper. I believe we did some experiment with a boosted variants, and I think we have some in our paper in the appendix. But honestly, I cannot be sure because over time we ran so many experiments. I don't remember what went into the paper or not. But yes, we definitely look into it. I think we have some results in the paper, but unfortunately, I'm not sure. And if you are, if you follow up with an email to me, I should be able to answer you this question.
Thank you. The next question is from Tan Lam. The question is, could you clarify what you meant by algorithmically simple?
Sure. So what we want is to be able, given a query point, given a query point, let's say the laser is a query point, wants to be able to figure out which let's say side of this hyperplane this point falls into quickly, right? Or if it's not a hyperplane, if it's a more complicated partition, we have to be able to figure out which part of this partition this query point falls into relatively quickly, right? Because we have to do it when the query point comes. So, we want this to be as efficient as possible, right? So for example, if you run neural network, the question is, we don't want this neural network to be too big, right? Because this affects the efficiency of the algorithm.
Thank you. The next question is from Andres Carrada. The question is, did your memory comparison for the count-min experiments include the resident memory of the classifier? What would happen if you do? Was it 2 times, 10 times the data structures? So did I understand the question correctly? Is the question, do we include the classifier size in our graphs, right? Yes, I believe so, unless, yeah, resident memory of the classifier. So if Andres, you want to clarify that.
Yes, so I did mention it briefly. So we do include it, but we include it in the amortized sense, okay? So basically, it's the same classifier, for it's the same classifier that we use for different runs of the algorithm, right? Let's say each run is a different minute. So we are amortizing the space across different runs, right? Which literally means that we divide the classifier size by the number of times we run this algorithm, and we add this amortized cost to this graph. Okay, we can, in a way, you can think about it as not as a random access memory RAM, but as a ROM. It's basically something which is sorry, which is hardwired into the algorithm, and it's the same for different runs of the algorithm, right? So we figured out that this is the most fair way of accounting for it.
Thank you. And we have a follow-up question from Samori. The question is, the choice of the classifier seems crucial. This relates to your second part of the talk, I believe. The choice of the classifier seems crucial as it needs to align with the geometry of the data with the partition shapes. How might that choice be done in practice?
Right. Well, so I can tell you what we did, which is we just went through the laundry list of classifiers that we thought might work. I wouldn't necessarily say that our approach was particularly principled. Let's see. In the end of the day, there are many options. You can use a neural network. You can use K-means. You can use, PCA tree. There are many options. I guess the consideration is the trade-off between the complexity of the classifier and the quality of the classification. Right? If you just use, let's say hyperplane, okay, I mean, it might work in some cases, but linear classifiers have their limitations, right? On the other hand, if you use a neural network, you can potentially approximate the original partitioning better, but the complexity, goes up, both in terms of evaluation, and at some point, once your neural network is too large, you might stop, you might not generalize anymore, right? So, I don't have particularly good guidelines, but, the things that we tried, are basically what I mentioned here.
Thank you. Now, maybe I'll ask one question while people are thinking of the questions to ask. Could you comment on perhaps, any value that you see from sort of trying to make the loss function the actual performance criteria that you consider, right? So for example, I guess in the first part, you would actually account for the count min algorithm, right? So you will take a look at the performance on that. And then I guess in the second part, you could account for that by looking at, right, what the nearest neighbor search algorithm actually does, right, while training your neural nets. Do you think that would, result in better performance, or do you think like perhaps, just this sort of, I guess, stage-wise procedure would be sufficient?
Yeah, it's a very good question. Right. So yeah. So I guess one option would be to use methods. Let's see. I briefly gave them some of them in the overview. Methods. Okay, I have to go all the way back. Like end-to-end style, right? Like use reinforcement learning. Yeah. My guess is that. And I should emphasize that this is just a guess. My guess is that one should be able to get better performance by incorporating the whole information. I guess the trade-off is between performance and the complexity of learning, right? Because like once you start using reinforcement learning, I mean, it comes with a cost, right? So that's one thing. The other thing is. I think in terms of understanding what the algorithm does, like this from our end, we find it helpful to decompose the process, right? So for example, for the count mean, we're able to theoretically understand what is happening, at least under certain assumptions. Now, once you train everything end to end, you know, you lose this modularity, so it's a little bit harder, you know, to reason about it, right? But as I said, you know, it's a little bit harder for us, you know, because we don't have experience with it. It's quite possible that, you know, for people that you know, are more familiar with reinforcement learning, you know, it's not an obstacle. Yeah.
Right. Thank you. And maybe let me just ask a follow-up question. Do you think perhaps this sort of stage-wise decomposition might be helpful in terms of, I guess, combating sort of this average case behavior, right, that you often get with learning? You know, I guess in the last plot you showed that, like, surprisingly, that the 95 percentile behavior is still quite competitive, right? Whereas I guess a learning-based approach is always looking at sort of average case, right? Like, do you think it might be like useful, perhaps, from that perspective?
That's actually a very interesting angle. I mean, we certainly didn't target it explicitly. Our improved performance in this like almost worst case was more of a side effect of what we did. But yeah, I'm guessing that you know, at the very least, we can reason about it. You know, this almost worst case performance if we decompose things. Yeah, but that's a very interesting angle, and we didn't think about it. Yeah, it's a good question.
All right, thank you. Are there any other questions? Okay, if there aren't many more questions, let's thank Piotr for the great talk.